No, we'll segue. Okay, my name is Wayne Green, and I have had the outstanding privilege of being with these most excellent people in the development of this project. I owe a particular debt of gratitude to COVID because it made us stay in our houses, bored out of our nuts, buying 3D printers and exploring this topic space. I'm also kind of thankful to SAS's support for encouraging us to sort of brand this thing under SAS, to use the material and so forth, internet capabilities of Zoom in particular to support both our project and the project that you'll be hearing about later on with some of the spectroscopy work that was done. Tom Smith was a member who sort of is in the background of all of it we have done. The experimentations early on, we have made an awful lot of mistakes to get to the point that we're at. And Tom really helped noodle us through quite a bit of that. His contributions, he was the one that has basically schooled us up on the 3D printing and those aspects. See if I get this right. Down is forward. Which way is down? Okay. Do I have it turned around wrong? There we go. Okay. So I actually managed to get the diagram on the wrong side. Automation. So when we talk about automation, what we're really meaning is if I'm the spectrograph sitting over here, you can be sitting anywhere in the world. And with the proper IP management and network traffic management, you can come. This is based on a type of browser technology. I'll go into the architecture here in a moment. What you're seeing on the screen, I know the laser pointer doesn't work for the people at home, so I tend not to do that so much. But what you're seeing is most of those thicker black bars represent gadgets within a widget. The gadget is something that you can design and put up there. So if you want to add an element to your spectrograph or to any instrument, really, you can follow the architecture. Across the top, you'll see some tab bars. If I hit one of the tab bars, it goes over to the Kaizen calibration. So that would be there are two pieces in the right-hand column there. And so what we have here is you can just tick the boxes. We had designed this so that you could either use it as an on-off, or you could add a slider for pulse width modulation, which gives you the ability to vary the intensity of those particular bulbs. And so here we show it like off and on, a few things on those lines. So the paradigms that we use, that was one of the things that was critical in user interfaces, is we use kind of the captain crew paradigm. So a lot of places go, well, gee, I need to move 47 steps. So rather than put in 47 steps and go someplace, a captain would sink a fleet if he tried to do that. He says, I want to go 25 knots. And the crew down in the engine room goes, 25 knots, that's 3,700 RPM. So they rev the boat up, the ship up, and off they go. So when I'm sleepy at night, I want to be thinking in terms of my science, not in terms of my machinery. So that was why we use that kind of captain crew paradigm. Within the architecture of the computer system, we have to move the information around. So what we chose, we looked at MQTT for a while, and we decided against it for a good host of reasons. Yes, it's a well-established protocol. Well-established protocols still have their issues. So what we went was a postmaster and patron type of a relationship. A postmaster is just somebody who you've got one in each of your towns have ones in your cities, your regions have one. We got some guy sitting in Washington that's the grand poobah. And so these guys work sort of semi-autonomously, independently. I, as a poor guy trying to send Tony something in Britain, usually I try to find someone at the airport who's going that way so that he gets it within his lifetime. But the idea is a patron, I hand it off to my local postmaster, and they begin to take on the responsibilities for addressing and distributing my information throughout the network. So we leverage, a good typo, wasn't it? The kind of the lower and Ethernet communications. And what this does is, as Tony mentioned earlier, it reduces our cable count down to 2. One for power, got to have power. Maybe we put a windmill on the thing. How about that? The other one would be something that carries the information, and Ethernet helps with that. You can put a lot of sub-protocols on Ethernet. 2 cables means we're not dragging around that forest of USBs. It also means that we can go anywhere in the world. And I defy you to buy off an eBay an USB cable that will stretch from here to London, okay? And the other thing that we do is we coordinate multiple instruments per mount or per OTA. So various postmasters can agree to work together, say, as a, what would you think of it as a zip code that has a lot of different delivery offices within it. And we can put these together with a Raspberry Pi that's placed up on the optical tube itself so that you don't have to worry about, again, that forest of wires that come down and do things. You can also, with Ethernet, have multiple Raspberry Pis on your OTA. Now, we chose the Raspberry Pi, which are now just about uninhabitable because of supply chain issues, but you can put any little small single board computer up there. The software is flexible enough, flexibility again, is flexible enough that you can adapt it to the architectures that you might wish to use. You can also segue into other protocols like Alpaca or Nina. We settled in with, I think it was, what was it, Tony? The Astroberry. You can buy the Astroberry or not buy it. You just download it, put it on your little card, stick it in the machine, and you're good to go. We rolled our own. You have the capabilities of doing that. You can file to fit as you may need. This also helps support the idea of piggyback photometry. It's an idea that for Sims and I have been kind of working on for several years. And that is where you're doing simultaneous, same mount, one mount, 2 telescopes on the same mount. One's taking photometry of a spectral field. We're staring at it for 1800 seconds. Might as well do something else while we're up there. Multi-band photometry and so forth can be done. All right, let's see. So in piggyback photometry, you can go through RB, what is it, BRV filters. You can go through any combination of filters that you might like that match your science. We had a discussion earlier about using Sloan's G and R near one of the cutoff points to measure shifts, broad shifts in the hydrogen alpha line for certain targets that are up there. I think, what is it, SS443 has got something like, what is it, 2,000 angstrom shift in its line, something like that. Yeah, and so the idea is that with the balance in this filter, you get a ratio analysis going on. Gives you incredibly low resolution information, but it gives you the ability to very quickly, photographically and photometrically, to monitor something like that. One of the traps of piggyback photometry, and this is something that we've been talking among ourselves while we've been here, a number of people that we've had the opportunity to go to dinner with, mismatched transform 0 points. Basically, if you go to AAVSO, you see a lot of differential materials up there. You're not quite sure how they transform their data, and that's critical if you're transferring that information, say, from ADU counts into ergs per centimeter squared second hertz or angstroms, I guess you guys work with. So unsubstantiated photometry from other sites. If we're not agreeing on how we're doing our transforms and we're trying to operate in a collaborative environment, or someone's relying on our data that we don't even know they're relying on our data, then that's a way that we have to be a little bit careful not to introduce errors. The other thing that I've seen that's been kind of critical is the idea that you want your mount as polar aligned as possible. A couple of us have really just shake our heads sometimes about that. What happens there is if you're out of alignment, even with your mount tracking software that will keep that pixel, your target centered on that pixel, your field will still rotate. So the external field rotation can do horrible things to you. It can mess up your point spread functions. It can also mess up your pixel statistics. So that's something that we beat into the ground during the workshop. Let's see, which way am I going this way? So just be careful when you start mixing your fruit in the fruit basket. Make sure you're at least got all apples in there. You may have Lisas and Macintoshes and things, that's fine. From a design perspective, you'll notice I've got 2 columns up here. One is kind of conceptual, the one on the left. One on the right is sort of a lot of jargon that says how we did it. We are data driven. We're not command driven, we're data driven. I make a statement, I'm the captain, I want you to go to 5,000 angstroms, and then that data goes over into the Arduino side of the house. It understands the mechanisms that it needs in order to translate that into how many stepper pulses to move from where I'm at to where I'm back. I'm not exactly going to make that translation correctly because stepper motors go in increments. So what it does is it now has a new state. It then transfers that state back to me, and then my user interface tweaks a little bit to say, you asked for this, this is what you got. Sorry, we hit a seagull, we're only going 24.9 knots. That kind of follows the RESTful protocol idea. I don't have any type of central location trying to manage the state of the entire host of things. We've already talked about the captain in the boat versus the astronomer in the code. Our architecture is a peer-peer relationship. So we use a package called Bouquet, which is a, excuse me, I call it Bouquet, it's actually Boca. It's the correct pronunciation of it. Don't worry, it's an inside joke, I guess. It handles the user interface, and it does so in a highly dynamical fashion. If I'm looking at a really, really huge, massively huge FITS file, it'll roll things up and only send things across the network that represent my ability to see it at my end. And as I zoom in, it'll change that view, and I can go down to where the pixels are this big on the screen. But that's the thing that Bouquet was designed to do. It's used throughout the kind of the data informatics arena. Millions and millions and millions of customers are using this thing. So it's a very, very stable approach to doing things. And in our case, what we do is we have this idea of a mirrored class system. Well, that sounds kind of inappropriate in this day and age. Up, wrong way, okay. So the implementation here is we're platform agnostic. We do use a little Raspberry Pi to do things. I tend to test on an Intel box sitting on my tabletop. I've forced some of this into a Docker container just to see where the wheels would fall off. So I can do it on my Macintosh. I can do it on my cell phone. I can do it anywhere I have access to, we'll say a Chrome compatible browser. Just about every browser out there these days is Chrome compatible, because all the guys that are using them are participating with it. We have an idea of the TCP/IP networking, but we also have a little sub information that goes along, which is a message to a postmaster. If he recognizes himself, he says, yes, I'm here. Do I have a patron that matches that within me? Yes. So the message then trickles down to the little mirrored class on the Arduino, understands the string that we're sending down to it. So we kind of followed a don't reinvent the wheel. We settled on Astroberry just because it existed. John Hoot's got some excellent software that you put inside of a virtual box. That's actually pretty interesting as well. We also kind of settled in on the K-Stars LibND ecosystem because the Raspberry Pi is primarily a Unix system. However, you can interface it from Win 10 very easily, and it has all the network communication that it needs to do its tricks. And also, if Bob will correct me if I'm a little bit off on this, but it allows you to use an ASCOM, and through ASCOM, the extension, the Alpaca interface, all that you're used to today. I seem to be dropping out a little bit. Is that just okay? I can't see anything now. Linux is a peer-peer type relationship. We do that. We're at the Arduino. No Ethernet connector. What's with that? You know, unless they use a dual whatever it is, dual Milo. We use a simple serial 3.3 interface. When we're on the card, and the Pi has this as well, we have the I2C interface, a whole bunch of other electrical jargon that goes along with that. Okay, keep going the wrong way here. In the postal system, let me see if I can help this out a little bit. What we have is a superclass called a patron, and it's a virtual abstract class. Okay, I'm saying this just so that you guys can kind of get a little bit of a feel for it. Virtual means it doesn't do anything except act as a placeholder. If I inherit that down by any of my other widgets, in this case, I've got the flex grading, which is the rotatable grading mechanism. It's a motor class that's limited in the scope that it can move. Otherwise, it bumps into things, as well as the collimator. That's the cam that can go continuously all the way around. And that would be like a full rotation motor. Further implementations that we would see a partial one, maybe a couple of winds in order to focus a commercial camera lens, or we would see another one that would go round and round that for making the slit choice, should we get around to implementing that. There's a little snippet of C++ code that shows you how that class kind of holds together. Arduinos use C++. It's not their own little coding language. You have to hold your tongue right a little bit to use it, but we have a massive amount of code running out there, lots of modules. And what we do with that is that we have to maintain it. We have to pay close attention to two things. One is that C++ 11 standard, which is a really old standard by today's means. The other one is we can't use any of the error handling capabilities. So, we just have to learn to survive and work around that. So one of the things that had happened was we had some Envision controls, the third bullet down. We got the collimator in there. We got the thing to manage grading angles in there. But you'll notice the unchecked box is work that we need to do into the future, as Tony indicated. We're not really happy with a glass slit. So we kind of left slit and slit automation to another time. Camera focusing. I don't want to get bit by the dog. So we don't have to implement camera focusing. We're not supposed to do that. Now, when we say we're not supposed to do that, we probably want to go ahead and have something in there, because if I'm the mountain engineer tonight, it's cloudy, I need to work with the device. I want to have some way I can tweak it, while I keep the dog, occupied in the corner with a pork chop or something. Guiding focus is something that we had talked about, just to accommodate those little small changes in guiding. With FlexSpec 1, the whole box is so small, we don't see that issue. If we go to something like an RF 5000 spectrograph, like one of our potential collaborating customers here would want, then we might want to have some way of tweaking that through the night. The crisper the guiding focuser or guiding images, the more accurate the guiding that we're going to have through the night. This thing also has a built-in IMU, which is an inertial management unit. As you go up under the sky, your slit's going to be misoriented with respect to what we call the parallactic angle. All we have to do is just very carefully put our unit together. So we zero out one axis, the axis of our choice. If we put our board this way, or this way, and it's just like, make that zero, parallactic angle is close enough, we can go. This very closely approximates what Mr. Sims had mentioned earlier about taking a plumb bob and hanging it off the back. It's so simplistic that the IMU built into the processor that we buy, all we have to do is leverage it. Keep moving away, sorry. Okay. We use an ARM core processor. They come in many flavors. There's one inside the Raspberry Pi. There's also one inside the Nano that we're using. There's one inside the XAL processor that we're using. So what we're seeing is that we're going processor independent, but yet we're relying on higher level programming, what would you call them, concepts, so that our code remains portable. We don't have to if, then, else, and all kinds of stuff to take care of those things. Okay, we started out, here's on my notes, 1800 UT is what, about noon, my local time. What time is it for you, Tony? It's 6 o'clock, isn't it? 6 p.m. So we were having a discussion and we drew out a basic object model diagram, and we stuck remarkably close to that. That's why I toss it in here. Okay, well, I can't do that either. So in general terms, the browser, the gray box that's kind of to the left of the white area there towards the top, that's your interface. That's the first slide that you saw with all of the snazzy colored buttons and whatnot. It goes into bokeh, Bokeh is a server. It will accept a number of attached places. As long as you've trained your postmaster to only accept things addressed to it, maybe with a little handshaking code, that means that, you know, the bad guy can't get after me, but anyone can help and collaborate with my observation period at night. I can take over Clark's telescope across town, say I need to tweak that. I can take over Tony's telescope across the pond. Let me help you tweak that. You know, and that way with the give and go, we can get better results. Everything goes back to one central additional separate server. That server understands the hardware that it's sitting in. So now we're beginning to filter out anything that we can't do. It owns the serial device that goes down to the little Arduino. We're so far out in the leaves right now, there's no way that we can talk to that Arduino by any other means. And as long as he's the right patron, happy day, we can process things inside. He takes the string that we give it apart, queues it up, sends it to a local dispatcher, and then off we go. So what we have is this idea of mirrored or shared classes. We have a Python on one side, we have C++ on the other. They understand each other. If I write the user interface one, I write the implementer one, and then I just split them apart and put them in their respective locations. Backwards way in here, okay. So what these things do is they allow us to have rule checking. They allow us to do, to make pretty good use of some very powerful programming tools, but errors are a bit of a problem. So we just declared them to be illegal, okay. The Python side, the user interface side, does all the rule checking. And it says, I am not going to send this message through the postal system, a letter bomb, if you will, that will take care of my Arduino at the other end. The Arduino is very trusting. It says, I trust this message is something I can deal with, and it will deal with it. And there can be a little bit of error detection and prevention in the code, but it's extremely difficult to catch it and report it back up. So we just made them illegal. And so the error code that would come back to you via Bokeh or Bokeh would come back from the Python side, not from the hardware side. Okay. Okay, the top one is forward. We don't use WIMP. What the heck is WIMP? That's Windows, icons, menus, and what's a P stand for? I don't use it. I don't like it. There it is. Pointing devices, I think is what it is. Okay. So we do everything through just implement that WIMP interface for you in terms of browser commands. That was one of the sticky points of this whole project. How do we write the GUI? And once we write it, how do I distribute it? If I distribute it, your machine's going to be configured different from their machine. And all of a sudden, we're the very reason that we're not going to make a business out of this. We'd have a customer that would complain. We want to keep all of those complaints to a dead minimum. If it's late at night, we just want it to work. We don't want to be getting phone calls in the middle of the night. It goes to the Raspberry Pi, and then through the TX and RX mechanism, it controls one or more devices. We even have ways that we can chain through the Arduino. For example, we can hang a Kazin ring off the Arduino, and because it's a postal subscriber to the postmaster in the Arduino, we can pass commands all the way down to that as well. This is our main program. It consists of two subroutine calls, essentially, or two class method calls. One's called the serial manager. We loop down to the dispatch manager. We loop up, we loop down. In the Arduino, Arduino has just this very simple looper as its operating system, and that gave us a bit of bother. The message comes through, goes through a state machine, and that helps filter out some of the lint. What we're using as a messaging architecture is just a simple JSON string, and that's being used pretty ubiquitous throughout most of the computing that you're doing. You brew something up on your browser, the state machine, the restless machine, state transfer, is done most of the time in JSON. JSON stands for JavaScript Object Notation. It's prevalent in Python, and through this Arduino, JSON Arduino module that you can install on your Arduino, they're the same piece of code. What I did is I took the Arduino C++ and I ported it back into the Raspberry Pi. So I changed complete architectures, operating systems, the whole thing. When I'm doing it with one set of code, so I don't have to worry about library inconsistencies in there. All right. The way the dispatcher works is, let's see, go that way. Yes, here's an idea of the state machine. If you send it an out-of-band character of the ETX, put 2 of them in there, the machine goes back to idle state. So I say easy way to recover from errors. I just say, please go back and pay attention, make a new string, and let's go from there. If it makes it through the state machine to the red box at the bottom, it gets queued and it gets sent to the dispatcher. This is kind of what the JSON string looks like. It's probably a little hard for you guys in the back to read. I'm going to, if you care about it, you know about it. If you don't, you probably don't need to read it. It is data driven. In other words, we're just matching these data templates, so it's not command driven. And it's been ported to where it's been ported. One more time, come on, here we go. One of the things that was interesting in this project for me, I've been in software engineering for 50 years. No, I'm not that old, 40 years. Is this idea of a Lambda function. And my question was, okay, Arduino, if you claim to be C++, will you stand up to a C++ Lambda function? And it does well. So that means I have a lot of power at my disposal. Okay, the details are in the slides. You guys can, if you care about it, and I know there are people out there that do, feel free to contact us, okay? Let's keep going over some of this here a little bit. Oh, one of the things I should mention here, in the code, we implemented, we put some stuff on GitHub. We use the Sphinx documentation package to write most of our documentation. We have a read the docs.io page on the other side, and that documentation system is incredible. What it allows me to do is to put up HTML pages that you can use through your browser. It also allows you to push a button and get a PDF printed out so that you can keep it at your desk or read it when you're offline, like where the internet doesn't go. We looked at MQTT. I won't go into the details. If you want to know more about why we chose not to do that, you can talk to us during the demo session coming up. So I guess in summary, what I'd really like to get into is the fact that we've taken a novel and new approach to doing things. If we were a business, we would want to interface with the rest of the world. We're just a bunch of guys having a good time. So we said, can we come up with better ways of doing it? We spent times exploring the optics. We spent a lot of time, what's going on here? We spent a lot of time trying to improve the optical path. We found that if we did not focus the collimator, we had slightly diverging or converging beams, which gave error in the distribution, the dispersion axis. On the software side, we said we want something that's clean and simple that we can test on the bench or we can test through the internet. We learned an awful lot from the automation phase, and we're still learning about it. And so we're still exploring new and novel ways that we can use this. We pushed the power up onto the OTA. The lack of an operating system on the Arduino meant that we built this sort of what I call a weighted round robin non-preemptive system. We have 2 calls, start something, and if you need a lot of time, you can't hog the CPU during just a simple little wait loop. So what you do is you just call us back with a little process I call think fast, which is something that was from IBM. It was called an IO fast release channel back in my early days when I was key punching my programs. And then that tells a scheduler, give at least that amount of time to the task and then revisit it when you get around to it. So I can go through all of my widgets out there and everybody gets a little time to catch up. And while they're catching up, or while a motor is moving or something slow like that, the rest of the machine has an opportunity to get things done. All of our stuff is currently in a system that I'm going to mention here because we've had a discussion in sort of the AAVSO world. We maintain private repositories. What happens in the repository stays in the repository. And we hash through things. We put bad ideas up there because often they turn into good ideas. The minute that we're happy with them and we're ready to share them, we move them over into a public repository. And that's the one that's public facing. Same goes with the documentation. So one of the things I'd like to do is to thank all of you for your support and say, I got one more slide here, I think. We have, I went the wrong way again, didn't I? Okay. Yes. There will be a demo later this afternoon. It'll be in this room. And I think James Singh's got something he wishes to demonstrate. There's probably 2 or 3 of you who have something you want to demonstrate. Greg's demonstration of the Kazin ring will be probably merged in with our demonstration of stuff there. So it'll be a one-stop shop for us. Look up at our little demo booth. So at this point, if there's any questions, be happy to take them. I'm going to ask that any particular things about the spectroscopy be deferred a little bit. We're going to have a spectroscopy discussion work group just coming up at lunch. And that way, John Martin can deal with the answers. Okay, questions, Jim.
Thanks, Wayne. Quick first question, just what's the name of the publicly accessible Git repository?
I believe it's FlexSpec1, STMSCI/FlexSpec1.
Okay. All right.
Okay, and I will put that information out for you.
Yeah, thank
you.
The second question, a little kind of niche, but you said you've got an IMU, right? So if you want to correct your parallactic angle, talk to your rotator, can you do that through Alpaca?
Yes. Now, you notice I had about 4 levels of how am I going to route that run through my brain.
Yeah,
okay.
Yeah.
The way that happens is we basically send something to a virtual patron that's up in the Raspberry Pi, and then it dumps it over in Alpaca speak to let Alpaca devices do whatever they need to do.
Okay, so it would require some little bit of code in the.
Remember do it DIY project? It's also a do-it-yourself code project.
Yeah. Okay.
Okay.
Thank
so
you.
One of the things that we chose this for, though, was to be open-ended and the ability to accommodate questions just like yours.
Thank you, Wayne. One thing that might be valuable to mention in the Astroberry part of that is that it includes a PhD 2 for auto guiding, which is an important part of the FlexSpec system.
Auto guiding isn't an important part of FlexSpec. It's awfully important to the spectroscopist because they want to make sure things track. So the one thing we did not want to do is to co-opt anything into our system. What we really wanted to do is to be as accommodating as possible of everything that is external to the system. And so I think it's John Wetmore is using an Astroberry derivative. Mr. Hoot over here, dang your hide, took me down the Odroid. I rolled my own and it worked just fine. So there's many ways that you can build an Astroberry equivalent system. I'm just using that right now as a placeholder and sort of a chapeau to the fellows that wrote that and giving us an excellent jumping off point. Other questions?